Hello students, welcome to Wallah English channel. In this session, I'll be discussing both the topics Turing motion and undecidability. Previous to this session, we know about the regular languages as well as context-free languages. Now, this will be the final topic and most important topic for the exam. If you look at the previous years, you will be seeing 3 to 4 marks from this topic, especially combined Turing motion and undecidability. Okay, let me begin with the Turing motion and undecidability, the agenda. We will learn about the Turing motion and how to construct. Then we'll move to undecidability, in which you will be learning different types of languages, like what is decidable and what is RE but not recursive, and also not RE. So 3 types of languages will be there in undecidability. We'll be learning there, and then important points which relates all the languages. Then we'll see some of the practice questions that can help you to think about the concepts. Okay, let me start with the Turing motion. So if you are aware of the Turing motion, right, of course, if you are aware of the finite automata, then you can easily think about a Turing motion. So let me explain what was the finite automata we had discussion earlier. So finite automata is having the parameters q sigma delta q naught f. If you have remembered, we have a tape which is a read-only tape and head can move one direction, and the finite control we have here, right? Finite control. We have head here, we have tape here, and this tape is read-only and head can move only one direction. So this was a configuration of finite automata. Then what is the configuration for Turing motion, which looks similar to this finite automata, like q sigma delta q naught f, along with on the tape you can read and write. Here you can only read, right? You can only read, you can't write, you can only read. Now you can also write on this tape. So now this tape is, you can keep bidirectional, but if you are going to keep the tape here, it should be finite tape. That input, whatever you store, the head can move only till the last symbol of the input. But here the tape is infinite. So your head, let's say your input is here, the head is pointing here, so this head can move any direction, and the tape bidirectional, so the head can move any direction, and you can read and write on the tape, and this tape is unbounded infinite tape. So now what we assume, everything except your input is just like blanks here. Here there is no such concept of blanks, because you have only the input that you have here, that's it. The head is going to halt after reading the B, no more the execution here, the finite control automatically stops, and this motion is going to halt at any cost. But this Turing motion, it may not halt sometimes, because this head can move bidirectional. If it happens, it is going to move all the time right, or it is going to move all the time left, or it is sometimes right, sometimes left, which is happening interleavingly. Then it is going to be never halt case. So sometimes this Turing motion may not halt for the invalid input. This head is a read or write head. You can read or write. Okay, so this is about the Turing motion. If you look at here, the other 2 parameters, the blank is a special symbol which is going to appear on the tape, just might help you to understand the below before and after input, so that you will know, are you crossing the input or not. Okay, do you want to use the extra the tape symbols of the tape, then you may use it with the help of that blank. And tau was here same as a sigma, because you don't ever cross apart from A and B, right? Here the apart from A and B, you can also write with new symbols, like A I can replace with X and B I might replace with Y. That depends on what you want. So the tau is the superset of the sigma here. So sigma is the subset of tau. Of course this equal is not required, we can say it's strictly subset of tau if you want it, but subset or equal, that you can say. Sigma is here A comma B, and tau here includes blank, as well as it may include, if you are replacing A with X and B with Y, the tau might be having the blank A, B. Apart from this, the A you may replace with X, B if you want replace with Y, maybe more symbols you can include in the tau, but here the sigma is only A and B. That's it. Okay, if you look at the difference between Turing machine and finite automata, if you give the power to the finite automata, the head can also write. It can also write on the tape. Now the head can move bidirectional. That means that finite automata can act like a Turing machine. There is no data structure like a stack or queue here. The tape itself, the tape should be unbounded. So look at that. The tape should be unbounded, that is infinite tape. The tape is earlier it was read head, now it is read write, and the head is bidirectional. Then it makes that finite automata is the equivalent to Turing machine when the tape is unbounded. And there are three restrictions that I am adding now. The tape is unbounded and head is read and write, and it can move bidirectional. So if that feature is going to be facilitated for finite automata, then this can act like a Turing machine. Okay, so try to understand the differences between finite automata and Turing machine. Okay, now when you compare this Turing machine with the finite automata, right, and PDA, so the two stack PDA, that means PDA already having one stack. If you give one additional stack to the existing PDA, that configuration or that power will be equivalent to Turing machine. So this is equivalent to Turing machine. And in case if you give two stacks to the finite automata additionally, if you configure the finite automata with additional two stacks, then this may act like a Turing machine. Okay, now 2 stack PDA can act like a Turing machine, then 3 stack, 4 stack, 5 stack PDA definitely act like a Turing machine, because Turing machine is already powerful machine in the world which can compute or which can represent some languages. Okay, now if you want to relate with other things like types of Turing machine, sometimes single tape Turing machine. Of course, what we have used here, single tape TM and multi-tape TM. You can also use multi-tapes along with multi-heads if you want it, or single head, doesn't matter. Multi-tape Turing machine. And what else you can have? Dimensional tape if you want to use dimensional tape like 1D, 2D, 3D, something like that. Dimensional tape. In this, one head may be sufficient for you to move up, down, left, right, something like that. So dimensional tape Turing machine, universal Turing machine. And you can also do that embedded programming here, universal Turing machine, and many types of Turing machine like one-way infinite tape, two-way infinite tape. So one-way infinite tape Turing machine. The single tape, further it can divided into like one-way infinite tape TM and two-way infinite tape Turing machine, single head Turing machine, multi-head Turing machine. Any such Turing machine, right? All are equivalent to Turing machine. That means this all are equivalent here. This all are equivalent itself. That means if you look at here, right? If you look at all of them, they're all going to be equivalent. There are so many types of Turing machines in the world, and you take a Turing machine, add any power to Turing machine, then you will get back to the Turing machine, because the equivalent power you will get back. So all these machines will represent the same type of languages, same number of languages, and they are going to represent same class. Okay, so what the normal Turing machine or standard Turing machine can do, all these machines also can do. May take more time or less time, but the power of the machine is going to be the same for all these machines. Okay, then what is this Turing machine? Right, we understood the configuration, we understood the types of Turing machines. Okay, maybe I'm not discussing any type of Turing machine more in detail right now. We'll just learn the basic standard Turing machine for many problems. Okay, now what is Turing machine? Okay, why we want to use the Turing machine? Okay, if you look at the finite automata to represent or to solve the regular problems, if you look at the push down automata, that will help us to understand the context-free problems, which might help us to solve the syntax programming of syntax of programming languages. Right, there are various applications with the help of PDA and finite automata. Like finite automata can also be used to design digital circuits. Right, the finite automata can also help us to design lexical analysis, and PDA can help us to implement or design syntax analysis, or can help us to solve the problems which are using one stack, only one stack I'm talking about, or no data structure at all. Fine. So these all are applications of PDA and finite automata. Now when it comes to Turing machine, all the applications of finite automata and all the applications of PDA are possible, are also applications of Turing machine. But what is the Turing machine? Right, what kind of problems it can solve or it can represent? If you have languages, what kind of languages it can represent? So Turing machine going to represent enumerable languages, that means recursively enumerable languages. So what are the Turing machine, right? The language represented by TM is recursively enumerable language, recursively enumerable language. If you look at the TM, right, the Turing machine, it accepts some language L. That L is called as recursively enumerable language. Let's say L is recursively enumerable language. How this Turing machine behaves? You give any input. This input, let's say W. Here the main issue with this W is it's not like what you have learned in finite automata. In finite automata, W is just like sequence of symbols, A, B, epsilon, something like that. But here this W can be a normal string, or this W can be a machine, this can be a language, this W can be expression, this W can be grammar, this W can be another Turing machine. That depends on what is your context or what is the problem that you are dealing with. So this Turing machine may take, may observe on multiple inputs also. This input might have the multiple parameters, all of them it can try to understand. Now you have given some input to this machine and this accepts some language L. And now how this behaves? It behaves like, if that string belongs to language, if the string W, input W belongs to L, this machine is definitely going to halt, and that too at final. Maybe which has exactly one path or at least one path, depends on type of the Turing machine, maybe deterministic or non-deterministic. There are two types of machines, right? If it is a deterministic Turing machine, definitely will be having exactly one path that halts at final. If it is a non-deterministic Turing machine, it will have at least one path that halts at final. But definitely it's going to halt at final using some definition. Halts at a final. Okay, that's all sure. In case the string is not belongs to L, it's an invalid string. If the given input is invalid, then how the Turing machine behaves is unknown. It might halt at non-final or it never halt. Either it halts, either this machine halts at non-final state, or never halts. These are the two behaviors. One of them might happen, depends on the type of the string. So now if the string is valid, it always halts at final. The string is invalid, either it halts at non-final or it may never halt. So these are the two situations will happen for invalid string. So invalid input. Now this is about the Turing machine acceptance. So this Turing machine is going to represent RL, but this is based on acceptance. But there is another kind of Turing machine. So this is acceptor, called as what? Acceptor or recognizer. This is called as a recognizer. So Turing machine try to recognize the language. And now there is another kind of Turing machine is enumerator. So Turing machine can also enumerate the strings of the language, like the strings maybe W, I, W, J, maybe anything. Let me write something else. I1, I2. Okay. Okay, W, let me write numbers 1, 2. No need to be in the order, just I'm writing the strings, and these strings are actually belongs to language L. So instead of accepting instead of halting at final. Now this Turing machine can enumerate the strings of language. That means indirectly we can say TM enumerates the language L. So all the strings that is enumerating are actually valid strings of L. So either way the Turing machine can understand a language. One way is by accepting the strings, another way by producing the strings. So this kind of machine is called as enumerator. What is this called as? The first one is acceptor, the second type is called as enumerator. It's trying to enumerate the strings of a language L. That L is called as recursively enumerable language. So this recursively enumerable language has many names. One name is, you don't need to use the word recursively, simply you can call enumerable language, or you can call recognizable language, or you can call acceptable language. All these languages are same and they are synonyms, and you can use any of these names to call REL. Recursively enumerable language has many names. Now you understood the definition of Turing machine. Now let's start designing Turing machine for some time, then we'll talk about other type of languages. Okay, before that, before construction of Turing machine, let me help you three things. Like, you have the Turing machine, and there are other type of Turing machines like halting Turing machine, and another type of Turing machine is a linear bound automata. This one is a Turing machine. When you restrict this machine, you will get the Turing machine that always halts, HTM. Halting Turing machine, the meaning is it is a TM that always halts. And LBA is also Turing machine, and it is HTM, but the tape length is linearly bounded. So this is a linear bound automata. It is HTM, no doubt, it is a Turing machine, and that always halts, but the tape is linearly bounded. Tape you cannot use non-linear. Tape length has to be, the usage of tape must be restricted to the linearly bounded. Okay. Now if you look at the differences here, this TM is going to accept recursively enumerable language. It means indirectly it can accept even the languages understood by HTM, languages understood by LBA. So this HTM understands or represents recursive languages. It accepts or represents recursive languages. Recursive language. Now this kind of machine is going to accept or recognize context sensitive language. Context sensitive language. Even though all the three types are Turing machine, but this Turing machine is more restricted, like it must be halting, it is using a linearly bounded tape. That's why the language is context sensitive. And even though this is a Turing machine, but that machine is always going to halt, and it is going to accept decidable language. Its name is, another name is decidable language. Recursive language and decidable language are synonyms here. And Turing machine accepts some language that is called as recursively enumerable. So here the decidable is REL, and even the context sensitive language is also REL. So you have a relation something like that. The CSL is the recursive is REL, but REL need not be recursive need not be CSL. So one way it is going to hold, like every CSL is recursive, every recursive is recursively enumerable language. Okay, you can keep that points here, but all the three machines are not equivalent in power. So if you look at the powers, right, the powers, first finite automata is having less expressive power than deterministic push down automata. Then PDA is having, if you compare these three, right, PDA will have more power and FA has less power. The reason is FA can only represent regular languages, but PDA can represent regular as well as some of the non-regulars. So after PDA is a more powerful one, linear bound automata, then more powerful one, HTM, then very important one that is more powerful than anybody here is a Turing machine. So this is a less powerful and Turing machine is more powerful. So if you look at the power of expressive power of the machines, expressive power. This is a less powerful, and Turing machine is a more powerful. Okay. And mostly what we are going to design here, we'll focus on only linear bound automata, but we call it as a Turing machine as it looks like a Turing machine, because this linear bound automata is purely depends on Turing machine definition only. But this machine always holds, and the tape is bounded. The size or space is limited to the linear. Okay, let's start the construction of Turing machine. Okay, let me start with the easiest problem here. The first one, construction. Okay, construct TM or linear bound automata or HTM that accepts language L, which is, let's say, A star. How do we design the Turing machine to accept the strings over A's? Now you need to accept epsilon, you need to accept A, AA, AAA, all such strings should be accepted. If you know how to design a DFA, NFA, you can easily convert that finite automata to Turing machine easy, right? Very easily. Now what are the strings are there? Epsilon, 1A, 2A, 3A, and so on. First, how do we read any symbol in the Turing machine? So in Turing machine, right, you want to read any number of A's, so you can do that by just taking the A we are reading, and on tape you must mention what symbol you are going to write when you read this A. So I'm going to write A, but no need to, as you never come back. If you don't want to come back, you want to go just forward direction, just mention the direction also. Right, R means right, L means left. So here A comma R means you are reading A, you are writing with A, and L means a direction. That might be right or left, that depends on your choice. Okay, so L, if I write R is the right direction, L means left direction. So these three parameters are very important, and you need to track the tape what symbols are modifying all the time, and why do you want to modify the symbols, because in tape there's the only way you can remember the symbols by writing with some other symbol. So here if I want to remember, then I might replace A with capital X, or A with small a with uppercase letter A. So depends on how do you want to remember it. So now any number of A's are there here, it's going to read with the help of one transition from this state, A's, it's going to read. When the end of the input comes, definitely after A star or before A star you will see the blank. So when the head is moving only right direction, because I'm always moving right, you will see the blank at the end. So when the blank comes, either with A's or without A's, when the blank comes, you can replace with the blank, move right or left, because you're going to halt right now. So maybe I'm moving right, but you can also move left, and you're going to halt, but you want to accept right, then you must mention with the double circle, which is the final state. But remember, this B is a very special, and once this B comes, you're going to halt, because there are no transitions here. There are no transitions here. Okay, this is how you design a Turing machine. Okay, if you don't want to use the blanks, you know that the head is only reading the input symbols, it never go forward sometime, backward sometime, it's always moving forward. Then what you can do, you can also make this a final state. After reading the all A's is automatically going to halt, but by definition the tape is going to have the blanks apart from your input. So you can always use this kind of final state. Whenever you want to accept it, just go to this special final state. Okay, like in PDA we were having like end of the input we were representing with epsilon, because once everything is over, at the end nothing is there, that nothing you can mention with the epsilon. Okay, so this is a very easy construction of construction of a Turing machine for the given problem. Okay, let me start with the second problem. Second, so can you try this? I want to construct the Turing machine for A power n, B power n. Okay, so let's try to understand how you want to design this, how you want to design the Turing machine. First you need to understand the logic, because when you are starting this motion, right, without a logic, if you start, you don't know how will you end up. There might be no logic when you design it. So first understand with some input like your string is, let's say, 3a 3b, and there are blanks before after, and your red is always going to start with the start symbol a, start symbol, whoever it is. And now definitely it should start with a's only, because a's and b's are there. If the a's and b's are not there, only epsilon should be there. So this head might be pointing to the blank when nobody is there, and when somebody is there, you will say a or b definitely. Okay, but as per our language, only a should be there. If b comes, we will not have a transition, means we'll go to dead state when the b is going to be there in the first case. Okay, now how you want to remember this or count this a's and b's, because you know the logic, a's and b's should be equal as per the given problem. So what is your approach? You don't have a stack to push onto the stack, right? You don't have a data structure apart from your tape. Now how you want to remember, this tape is more powerful than a single stack and more powerful than a single queue. It is having more power. You decide how do you want to use it. Now one logic is like scan, but in first scan 1a 1b you replace with the new symbols, so that you know that when you come back, that 1a is already over. That means you will try with the second a, and when you go second scan, second a second b, you can do with some other symbols, you can replace with some other symbols. Now when you come back, and in third scan, third a third b will get be override with the other symbols. Now when you come to the fourth scan, then you will never see the a. Indirectly you should guarantee there will be no small b. Then you go to the final state. So look at how you are going to implement. So now you are going to do multiple scans. In each scan, the 1a 1b you are going to compare. Like in the first scan, this a will replace with x, let's say this b will replace with y. And in the second scan should be from here somehow, and second scan, this a and this b should be tracked somehow. Okay, this a should be replaced with x and this b replaced with y. And a third scan, in the third scan, and from here this a and b should be replaced with some new symbols. And when you are trying for the a's, you will never find here, because a's are over, then b's must be over. So what should be the logic to understand the number of a's equal to number of b's? So let's go into deeper, try to understand how many states required, and accordingly you just design it. Now I'm going to do one thing, that first thing is the 𝐻0 is going to replace a with x. So I'm going to take care of the functions like 𝐻0 job is to replace a with x. Okay, that's all the job of 𝐻0. And what is the q1 job is, the 𝐻0 will hand over to q1 will try to find the b, but you can't find alone. To find the b, you might see this y, or you might see this x, and x you will not see, you will see the a's here. So to find the b, you might have the a's after replacing a with x, the next, because you are moving right direction right now. So find b, but how do you find a b? By skipping all a's and then y's. So to find the b, you may require to skip or to read the a's and x's. X or y, y's, because before the b's you will see the y's. Skip a's and y's, then only you can find the b with the help of the q1. When q1 sees the b, right, it will replace with the y, b will replace with y. Find b and replace with y. That is the job of q1. It will give to q2. So what is the q2 job? And q1 is not going to allow you to move right. Now q1 says I'm moving left because my job is over. Then q2 is going to do the reverse scan, but q0 is going to get the position that of a. So how do you find the position of a? Basically, let's say this is the first time a replaced with x, and where is the next a? This one is the next a. But how q2 knows? When q2 scanning in the reverse direction, it will get to know the after the first x in this direction, if this is the first x, then after that a should be there. If this is the first x, after that a should be there. Okay, it's going to find the first x in the reverse direction, so that it will hand over to 𝐻0 by moving right. Then 𝐻0 can start the whole job similarly what you have seen here. So Q2 job is to find the first x in reverse direction, so that it will get to know the next symbol the 𝐻0 can read to proceed the same approach. Okay, now how it's happening, just look at once, then we'll design a machine. Suppose you have A, B, 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 right? It starts something like this. 𝐻0 will start here, will replace A with X, and immediately moves right and gives to Q1. What is the Q1 job? To skip A's as well as Y's, because first time you don't see the Y, because there are no X and Y in this first time. Okay, we are going to write with X and Y. Q1, it's going to read all the A's so that you can reach the B. Then Q1 job is to replace B with Y. Then immediately give to Q2. What is the Q2 job? Q2 is going to start scanning in reverse direction. From here, it's going to scan reverse direction, but to find the first X, this one is the first X, and immediately it gives to Q0. What is the Q0 job? Q0, it will start from here again similarly what you did, and Q0 will replace A with X and then gives to Q1. Q1 skips A's and Y's to reach the B, and Q1 replaces B with Y and then gives to Q2. Q2 reversely it scans, and this will be the first X in the second scan, so it will give to this A by handovering to Q0. So this whole job is repeated to find the equal number of A's and B's. What happens at the end when Q2, once this B job is over, right, B replaced with Y, then it gives to Q2. Q2 will try to find the A. Before that, the first X it is going to look at. This is the first X because all the A's are over. When this is the first X, and immediately gives to Q0. Q0 is not able to see the A. Q0, when it sees the Y, it means if Q0 sees the Y, it means all the A's are written with X. When that happens, if there is no A from Q0, then Q0 is going to hand over to some state, dummy state Q3. Q3 job is to see only Y's are there. If Q3 can reach blank, then it can go to final. So this whole story is just like a program. So as long as you don't provide your own logic, you cannot design the machine. Here machine designing is not important. The way you design a machine, you should know before designing it. That's all. You should make a proper logic, how you want to accept this input, right? How many states you want to keep, and how do you want to rack them. All depends on which example you take. Okay, take the bigger example so that each step by step you will understand exactly how you want to compare. Okay, so with this, I hope you got a logic what I'm doing here. I'm going to do something here, okay, that I will explain with the machine. Q0 is the initial state which always sees A's when A's are there, otherwise it sees the Y. When Q0 sees the Y, that means all the A's are done. Now Q0, when it sees the A, it replaces with X and moves to the right. This is the first job it has to do. A replace with X and move right. But where it gives to Q1. What is the Q1 job? Q1 job is to find the B when it is scanning forward direction. So to find the B, it has to skip so many things. A's might be there just after the this A written with X, then so many A's might be there, just move right. If this is not going to happen, and after some time you will see the Y's, when Y's comes you move right, because on B you are going to replace with Y. This is where the 1A 1B matched. So this A replaced with X, and in between anything is there, you skip, and when the B comes you replace with Y and move now left, because once complete scan is over. After replacing with B, don't go to the right direction because you don't have a C's to compare. If the problem is A power, B power, C power, N, then definitely you can go forward and then you search for the C. But now you don't have any other symbol other than A and B. So what you do, now Q1 on B, you replace with Y and move left. So now Q2 will take care of reverse scan. What is the job of Q2? To find the first X in the reverse direction. To find the first X in reverse direction, what are the things it has to do? Suppose it's assume that Q1 replace just B with Y and Q2 got a control, then Q2 has to skip the Y, and if there are any A's, skip and to find the first X. So many things it has to skip. Skip Y, that Y left, and skip A's if there are any A's here. And when it sees X, it will not go, it's going to skip, but what it does, it takes the right turn and gives to Q0. So now Q2, when it sees X, now it knows that after this X, A might be there. If A's are left, then this X will skip. That means X with X only, but move right. So this is the key point, how Q2 knows the how Q2 knows when the control should be given to Q0. When will it be? When X comes in the reverse scan, then give just control to the Q0 by moving to the right. Then Q0 will get to the A position, then starts doing the same job. Every A will count, or every A will replace with X, and similarly every B will replace with Y in every forward scan. In the reverse scan, the Q2 will take care of how to hand over to Q0 by giving in the proper position. Now this is going to happen for all the A's and B's. Like 3 A's are there, 3 B's are there, then all of them replace with X and Y respectively. So when the machine should alt at final. So when Q0 is going to point, because Q2 doesn't know that A's are there or not. So Q0, if suppose pointing to Y instead of A, because A's are over, right? Now Q0 is pointing to Y. That means you should aware that all the A's are written with X. That's why you reach to the first Y. Now Q0, when it sees the Y, then it knows that all the A's are done, but B's we don't know. B's might be left. Small B's might be left. You do not know. You should check that. So now move right and give to some state. If only Y's you skip, you should reach the blank. If blank you are able to reach after skipping all the Y's, after reading all the Y's, then that means number of B's equal to number of A's. If only Y's are there, then you must reach to the final state only on blank. If the blank comes, move right or left doesn't matter. When the blank comes after just skipping the Y's, that means the number of A's equal number of B's. That is the reason there is no B left. Suppose from Q3, if you see small b or small a after the Y's, that means you don't have a path, you don't have a transition, that means goes to dead state. So that is not going to be accepted. So this is the final state. In case if you want to accept epsilon here, directly the Q0 will see the blank. When Q0 sees the blank, directly you come to the final state, because that epsilon, if you want to accept epsilon, then this is the way you can do that. Other than the epsilon, any non-empty string which has A's and B's should take this path, and finally it will go into this path. Okay. So this is the machine which accepts equal number of A's and B's when the strings are having in the form of A's followed by B's. Okay. Now let's try the third problem. Similarly, you can, I'll give you a logic, just you try. L is equal to A power n, B power n, C power n, where n greater than or equal 0 or 1, you decide it. Okay. So how do you plan now? It's, you have lot of A's and then B's, then C's. So do not look at only the first scan, because first scan you don't have any new symbols. So if you go to the second scan or third scan, you will easily understand exactly what symbols need to be skipped and what symbol you are looking for. So after some time, I'm just writing directly. After some time, this will be a position, right? X, let's say A, and Y, and B, let's say G, and C blank. So after some time, this is going to happen, because every A you are replacing with X, every B replacing with Y, C replacing with G. Now, what you are going to do? So look at here. If the Q0 is going to replace A with X, immediately it should go to Q1. What is the Q1 job? To skip A, to skip Y, then to reach a blank, B. So here you need to skip both A and Y. Skip A as well as A's as well as Y's. Two things you need to skip to reach the B. Once Q1 reaches the B, it replaces with Y, and previous problem you have taken the left direction. Now you should not, because there is a C there to compare. So it takes right direction but gives to Q2. Now earlier Q2 was doing reverse scan, now Q2 cannot. Q2 will do the forward. Now Q2 job is to find the C, but to find the C, what need to be skipped? It has to skip B's as well as G's, B's and Z's. Now Q2 when it sees C and replace with Z and gives to Q3. And what is a Q3 job? Q3 job is to skip so many symbols, like it has to skip Z, it has to skip Y, B, A to reach this X. Here it is a X, right? And Q3 to reach here, it has to skip lot of symbols, like first it has to skip Z's, then B's, then Y's, then A's, then only you can see the X here. When Q3 sees the X, it knows that it should give to Q0. So this whole procedure will be repeated. Q0 will start here. The whole procedure will be repeated for A's, B's, C's, like equal number of A's and B's and C's. Now at the end, what will happen? When Q3 has given to Q0, instead of A, if it sees the Y, that means all the A's are written with X. Indirectly, all the B's should be written with Y and all the C's should be written with Z. So now when Q0 points to Y, then go to some Q4 state and skip Y's and Z's only, no other symbol. Skips Y's and Z's so that you should reach the blank. If you are not able to reach, the string is invalid. Suppose extra B is there here, or some A is there here other than B, extra, that other apart from this Y's, then here you don't see any transition from that Q4 state, so it blindly goes to dead state, you can assume. Okay, so this is how you are going to design. Okay, and I've just helped you to understand. So let me design the machine, just to think about how to do the homework on your own. Okay, so let me start. Q0 job is to replace A with X, take right direction. And what is the Q1 job? Q1 job is to skip A's and Y's, So A right, and then other symbol is Y, right. So when you skip both of them, you can reach the B. So when you reach the B, you replace with Y and take right only. As you have a C symbol to do that, to match. What is the Q2 job? Skip B's and Z's. Skip B's and then Z in the right direction only. If you do them, then you should reach the C. And when it reaches the C, then replace with Z. Now once scan is over, take left direction. What is the Q3 job now? Q3 job is to skip everything in the reverse direction, like skip Z. How do you do that? Z left, and skip B left, skip Y left, and A left. If you do them, then you will reach the X. Then just take a right, because now you are going to take a forward direction. Now one forward here till here, and from here in reverse, and from here once it is reverse is over, then you will take a right turn. That means now again forward is going to begin. The forward scan, the reverse begins, then again forward scan, forward and reverse begins. Okay, so this will take care of all the A's and B's and C's are going to be written with the X, Y, Z respectively. If all the A's are over, then Q0, other than seeing A, it will see Y. When it sees the Y and go in the forward direction, because now the job is over, Q0 job is over, then Q0 is going here, that means there is no A left. Then what it has to do? It has to skip B's and C's. Actually they are not B's and C's now, they are Y and Z. So now you are going to skip from Q0, go to some new state, let's say Q4. Q4 is not there, right? Go to Q4 and there you skip Y and Z. Y right and Z right. So skip Y and Z. Now what you do is, if only Y's and Z's are there, definitely the Q4 reach the blank. Q4 reach the blank. When it reaches the blank, then just replace with the blank or do anything and move any direction, doesn't matter, but go to final state. Go to final state. And here you want to accept epsilon. The one path you should ensure that from Q0 directly blank come to final, because there is no input there. Okay, especially epsilon you want to accept, then this path is necessary. Okay, so now you see that this machine is going to accept A's followed by B's followed by C's, where A's and B's as well as C's are going to be equal. Okay, so this is how you design a machine, a Turing machine. And now this Turing machine, very powerful. What it cannot do. Let's see, some other than the accepting the strings, right? You can do some things like functional device. One's complement. Of course, you can do two's complement. You can do binary addition. I'm not doing all, but you can try. See, one's complement, right? What is your target? Initially, you have some input like this on the tape. Of course, blanks are there before, after. Okay, now head is pointing here. Your job is to replace this 1 with 0 and move forward 0 with 1 and move forward 1 with 0 and move forward 1 with 0. So after doing this, the machine is going to halt. There is no concept of final and non-final here. The job of this Turing machine is doing one's complement, like it's going to produce what you want. So now the input to this Turing machine is 1 0 1 1, and this TM will produce 0 1 0 0. Okay, now you need to do assumptions really if you want any, but if you don't have any assumptions, just start designing. So how do you design? Just initial state can do that job. 0 replace with 1, take right, and 1 comes, then replace with 0, take right. If only these two transitions we are going to perform for the initial state. When the blank comes from Q0 initial state, okay, from Q0, when the blank comes, replace with the blank and take right or left, doesn't matter to us, but blank replace with the blank and say just halt, because there is no acceptance here, there is no valid invalid string here. Every string you have a corresponding output. So every string is going to be very important for you. So we don't consider any valid invalid cases here. Only we do what is the output for corresponding input. So this kind of Turing machines don't have the acceptance behavior. This Turing machines will have the functionality behavior. They are going to halt after performing their job. Like one's complement, as I said, two's complement, and then addition of binary number, multiplication of two numbers, and what else you can do. Okay, if you want to compute any 2 power k, so k you can give an input. If you want to perform n square, if you want to perform square root of n, if you want to perform the prime, so any kind of such things can be done with the help of Turing machine, but may take much time, may take more states, but depends on your problem, the machine going to be designed. Some machines you need to perform the functionality. For some machines you want to recognize the given input, and you want to check the given number is prime or not, the given number is even or not, or you want to perform the computation like addition of two numbers, give the inputs and will produce the output. Okay, so likewise you can design a lot of Turing machines, like you can design Turing machine for any regular language, you can design Turing machine for any context-free language, you can design Turing machine for any context-sensitive language, and Turing machine can design beyond that. It can be designed for recursive languages, it can be designed for even all RELs. Okay, mainly Turing machine is going to cover all the languages which are there in the Chomsky hierarchy within type 0 class. Okay, type 0 class. Okay, now we have, let's say we have two languages here. What are they? Recursive and recursively enumerable. So let me start with that. I did not discuss the name earlier much, but recursive language. How it is different from recursively enumerable language? Recursive language is accepted by Turing machine. So this is equivalent to halting Turing machine, equivalent to halting Turing machine. So recursive languages are having always halting Turing machine, but REL may or may not have halting Turing machine, but they have Turing machine. So these languages are always having Turing machine, may or may not having alternate Turing motion, but these languages are always having alternate Turing motion and always having Turing motion. So here Turing motion is not important. Which motion? The Turing motion that always false is important here. So for this language, what exists? HTM always exists. Indirectly TM exists. But if I say only TM exists, that's not going to have a meaning. You know, when you look at this, right, you can say that Turing motion exists because of HTM exists. Okay. REL means you can't say HTM, but you can say TM exists. When for any language, if TM exists, for any language, if TM exists, you can say that languages are real. Maybe that language is regular or context free or context sensitive or recursive, doesn't matter to us. If TM exists, that is real. Maybe finite language, maybe regular language, maybe CFL, doesn't matter to us. It could be any of that languages. But now here, if that language is recursive, here, see that it might be regular, it might be finite, it might be CFL, but here non-recursive you cannot take here. There are in this RELs there are two types of languages, recursive languages as well as non-recursive languages. So if you want to see the classification, right, see here, these languages are called as recursive languages. All recursive languages are here. All recursive languages are here inside. Infinite languages are there, regular, CFLs, DCFLs, all are inside. Okay. Now what is this recursively enumerable class? This is all RELs. All recursively enumerable languages are here. Now if you look at this classification, right, this class is inside, the blue box is inside the yellow box. It means every recursive language is REL. And here you compare, this is very special. This language is not just REL, it is outside the recursive class. It means it is not recursive but REL. So you can say these are different languages, all RELs which are not recursive, but they are not recursive. What is the meaning of this? The meaning of this is they will have a Turing motion, but they don't have HTM. These languages are having HTM, so hence they will also have a TM. But these languages are having TM, but they don't have HTM. So here three types of languages are there. Recursive, HTM always exists. REL but not recursive, TM exists but never have HTM. And REL, maybe recursive or maybe not recursive. There are two types inside. So REL, we can just simply say Turing motion. HTM may exist, HTM may not exist. Doesn't matter, but TM exists for both kinds of languages. So that is the main important relationship. And apart from this, recursive languages are accepted by HTM and decided by Turing motion. That's why these languages are called as decidable languages. And here, these recursive languages are enumerable in a particular lexicographical order by a Turing motion. So if any Turing motion is enumerating the language in lexicographical order, example, if you are having prime set like 2, 3, 5, 7, 11, if you are able to enumerate in lexicographical order, that set, the whole set of prime numbers, you can call it as recursive set or recursive language. In case if you have any language which is either lexicographical or non-lexicographical order, doesn't matter. If TM is enumerating any set, that set you can call recursively enumerable. It means if TM is enumerating in lexicographical order, that you can call recursive, and every recursive is REL. So here you remember that one point, first point, every recursive language, every recursive set is REL. You should never forget this point. It means this recursive, another name only, decidable. And that REL, another name only, semi-decidable. Okay, every decidable language is semi-decidable language as per the statement. Every recursive is REL, but REL need not be recursive. Maybe not recursive or maybe recursive, depends on which type of language that you are talking about. Fine, this is the first point. And second point, Here REL, if you take, need not be recursive. In the converse, you cannot say REL is recursive. If example is given, clearly you can say which language, but in general REL may or may not be recursive. But every recursive is REL, because every recursive is having HTM. When you have HTM, you will be having TM, because every HTM itself you can call TM. That's not an issue. But if you have a TM for a particular language, but that may or may not have the altering Turing motion for the same language. Depends on the, again, type of language, or depends on the language exactly what you take. This is about the difference between recursive and REL. So when you consider these languages, right, there is a very important topic on them, closure properties. There is very important topic, that is closure properties. I'm only talking about very important closure properties for recursive languages and closure properties will be also seeing here RELs, recursively enumerable languages. Closure properties for recursively enumerable languages. If you look at the properties, right, here there are so many properties, you know that. Some of them I'm discussing here, not all. Union, intersection, complement, okay, 4, difference, concatenation, reversal, 𝐂𝐤𝐴 star, 𝐂𝐤𝐴 plus, subset. Okay, just take important operations. The same we'll be having here, but what are closed and what are not closed here? In this, union closed, intersection closed, complement is closed. Because of these three are closed, right? So now difference depends on complement and intersection, and also union if you want, right? So difference is closed. And concatenation, reversal, 𝐂𝐤𝐴 star, 𝐂𝐤𝐴 plus, and subset is not closed. So here the most important one is a subset. Subset is not closed. Okay, not only subset, you know, there are many other operations like substitutions, substitution homomorphism, okay, and various language, various operations are there which are not closed. And among this 9, the subset is not closed for the recursive languages. Now let's look into the RELs, recursively enumerable languages. Union, intersection, complement, difference, concatenation, reversal, 𝐂𝐤𝐴 star, 𝐂𝐤𝐴 plus. Anyhow, subset is not closed for all these domains, right? Regular CFLs, DCFLs, CSLs, recursive RELs. That property is very easy. They are not closed. The subset operation is not closed for all these domains. But here the union, intersection both are closed, but complement is not closed. Hence, even difference is not closed. But this all operations are closed for RELs. So here you can remember three operations: subset, complement, difference. These three operations are not closed for RELs. Okay, keep this note. Okay, these are closure properties for recursive languages. Among them, subset is not closed. And here closure properties for recursively enumerable languages. Here the complement, difference, and subset. And if you want to go for more operations, yes, you can consider them and you can include in this list and look at them which are closed and which are not closed. But this is the very important list for exam, where you see the most of the questions from recursive and RELs lies in this closure properties, okay. Now let's, among these operations, right, complement is one of the important operation for understanding the next topic, undecidability. So there I'm going to focus more. So to understand undecidability or decidability, first let me discuss with you the complement operation over these two languages. So here for that I'll just write a few points so that I'll answer at the end. Let's say I have a recursive language. Recursive, one language only. What is the complement? Okay, we'll find the answer at the end. And REL, recursively enumerable language complement, what will be the answer? And there is another language REL, it is REL only, but which is outside recursive, that is a but not a recursive language. This is a one language name. What is the complement of this one? What is the complement of this one? Okay, these three languages are very important while understanding the undecidability. So before that, let me answer these questions. Now, recursive languages are closed under complement. Recursive languages are closed under complement. So complement of recursive is a recursive. So now these languages are recursive, right? All recursive languages are here. All recursive languages are here. All recursive sets. Infinite recursive languages here. Now, this yellow box, right? Yellow box is about all RELs, including this blue box is also inside. All recursive, all RELs, recursively enumerable languages. Now we have one more class, that is this one. From here to here, we call them as all RELs which are not recursive. When you look at this, right, here there are infinite languages, right, and here there are infinite languages in this whole box also, because this infinite will be definitely infinite. Now I'm going to talk about three languages here. If I take one language here, let me take one language here. Here I'm taking one language, let's say L1. If I do the complement here, right, you will get inside itself, because recursive languages are closed under complement. You take any language from here, then do the complement, you will get here itself. So that's why recursive complement is recursive. Is recursive. But now REL complement. See, RELs are not closed under complement. Doesn't mean that not REL. Maybe, may not be here. REL complement. See, this inside this yellow box, REL may be here or may be here. If it is here, then its complement lies here only. If it is here, this language is only the problem, because this languages, for these languages, valid strings will have a logic, but invalid strings we can't create a logic at all. Right, we can't stop for all the strings. That makes an issue. The L2, in case if the language is like this one, REL but not recursive, if this is, let's say, L2 and this language complement goes here, it means this language name is not REL. So here the answer, REL but not recursive complement, is going to be not REL. Will never have a Turing machine for L2 complement. So even though L2 has a Turing machine, but L2 complement will never have a Turing machine. But L1 and L1 complement both will have a Turing machine. In fact, both will have HTM also. Okay. Now REL complement. See, now REL, see, if I take this language, complement will be recursive. If I take this language, complement will be not REL. So answer lies here. Answer lies here. So is it not REL? Or is it recursive? So that depends on which language you take. You take any language from here, you will get a recursive. You take any language here, that gets not REL after doing the complement. So REL complement, you will see either recursive or not REL. But it is true, it is guaranteed, never be REL but not recursive. After doing the complement of any REL from here, the language will never come to here, right? Will never come to here. Either it will be here or it will be here after doing the complement of any language here. Okay, so that's one of the important point which was asked directly in the exam so far. Okay, you can see that PYQs, you will see one of the question, REL complement is never be REL but not recursive, because this REL's complement will be here only, this REL's their complement will go outside. That means in this yellow box nobody coming here after the complement. Okay, that's one of the important points. Now with this we have understood what is a Turing machine. With this knowledge we can start undecidability. Okay, in undecidability languages, or in undecidability problems, we have two types. But anyhow, we'll just look into a broader perspective, languages, how we categorize. So when you have the language, right, or languages, we categorize into three types to decide what type of language it is. Okay, three types. One is called as decidable language, or languages or problems. Sometimes we take consideration of the problems, or sometimes languages we consider. Now decidable, okay, what is it? A decidable language or decidable problem. Another one which is recursively enumerable, but that is not recursive. So clearly you should know that these two languages, even decidable, another name is recursive. These two problems or these two languages comes under recursively enumerable class. So both are called as recursively enumerable, but inside the recursive enumerable we have recursive, we have not recursive. But this problem is decidable, these problems or these languages are not decidable. In fact, they are undecidable, but here also there are some undecidable. So this class or these languages are not RELs. So this two comes under undecidable, this two comes under REL, and this comes under decidable. So here you need to know, don't put in the bracket here undecidable, because these two are called as undecidable. Not only this, even this one called as undecidable. So these two languages called as undecidable. So undecidable are two types. Undecidable are two types. So one is decidable, other one is undecidable. This two comes under undecidable. Okay, undecidable. So whether it is RE but not recursive or not REL, you should call it as undecidable. But this has many synonyms. Okay, these two are not synonyms. Undecidable need not be RE but not recursive, but RE but not recursive is always undecidable. So understand the statement. But this has many synonyms. RE but not recursive, you can also call it as SD and UD. SD means it is REL, UD means it is not recursive. Undecidable means not decidable. SD and UD. And this one UD but not SD, you can also call it as UD, it is undecidable only, but which is not REL. Not REL means not SD. So this is UD, these both are undecidable, but this is semi-decidable, but this is not semi-decidable. It has a Turing machine, but it will not have a Turing machine. That's all the difference we have here. Okay, but this one is the decidable, will have alternating Turing machine, will have Turing machine, and many ways you can speak. Okay, this is a classification of the languages. Okay, always we focus on these three. So when somebody asks about REL, these two are RELs, are recursively enumerable problems. And when somebody talks about undecidable, then these two are undecidable. So in the exam, so you should be very careful. When they say REL are basically two types. One is a recursive, which means decidable. Other one is not recursive, which is REL but not recursive. In fact, the name itself is, we say, REL but not recursive. Okay, better to write that way. REL, which is not recursive. It means you have a TM but you don't have HTM. This one you have TM as well as you have HTM. And when it comes to undecidable, undecidable is two types. One type is this one, other type is not REL. So you should know how do you classify. These two are very dangerous sentences or words, because when you say REL, you will not have a clear sentence. That is, are you talking about decidability or are you talking about some undecidability class, that is REL but not recursive. When you say undecidable, you are not having clear again, you will have a Turing machine or not, because even though you have a Turing machine, that languages are also called as undecidable. Even though you don't have a Turing machine, you will also call them as undecidable. So you should know the clear definition of these three. The decidability means HTM exists. In fact, Turing machine exists, but main concern is about HTM. And for this, TM exists, but we don't have a TM. Definitely we are saying and no HTM exists here. No HTM for them. But here, no Turing machine at all. It means no HTM also. Okay. So these are the three important definitions for languages as well as problems. Here I have taken the languages, but you can also consider for the same problems. Okay, now what is most important, the concept in undecidability. In undecidability, there is a one concept like, decision properties table. If you are aware of the decision properties table, you can learn or you can answer many questions in undecidability. Okay, that property or decision properties table I'm just drawing here, but you go and do research in the table if you want to know about the complete table, but I'm just mentioning the important points here. Okay. One is halting problem. Other one is a membership problem. Emptiness. Finiteness. Totality. Equivalence, disjoint, and set containment. So total 8 rows are there here. Let me write the names. So here the problem name that I am going to write here, the problem name. So we can call this table is the decision properties table. What is the name of the table? Decision properties table. Decision properties. So we'll be having the problems to decide whether they have halting Turing machine or not. Whether they have halting Turing machine or not. First we'll have the column for regular languages or finite automata. Then we'll be having DPDA or DCFLs, or we have PDA, and then we have both LBA Turing halting Turing machine. You have the same column here. Okay, let me write one by one. So this is about the finite automata or regular languages. or regular grammars or regular expressions, DPDA or deterministic context free languages, and PDA, push down automata or context free languages, linear bound automata. I'm just writing HTM as we don't have the syllabus for linear bound automata. Let me write HTM or recursive languages, REC. Okay, assume that recursive languages, and Turing machine or RELs, recursively enumerable languages or recursively enumerable concept. Now the first problem is called as here the halting problem. Very famous problem is halting problem. Whether the given Turing machine or given finite element or given DPDA, given PDA, given HTM halts on a particular input. So here two inputs will be given, machine will be given and input will be, the string will be given. So you need to understand given machine will halt on a given input or not. So up to HTM, because then all these machines always halts, only the Turing machine has a problem. That's why this are going to be decidable. Okay, these are going to be decidable. Anyhow, I'll write at the end. So let me write the problem names first. Halting problem, and the second problem is membership problem. Membership. So whether the given input is accepted by given machine or not. Emptiness, given a machine, is it accepting empty language or not? Empty string is different, empty language. This is about empty language. Okay, there is no string should be accepted by the given machine, then we say emptiness. And finiteness means finite language. Is that given finite automata accepting finite language or not? A given DPDA, is it accepting finite language or not? So we have, for every column the input is going to change. Okay, but problem definition is same, but a machine is going to change, machine or language. Other one is totality. Totality represent the completeness. Completeness means if I give you finite automata, then is it accepting every string in the sigma star? That is the machine accepting all the strings? Then we say totality concept. Okay. Disjoint. Disjoint problem is, I'll give two machines, two finite automata or two DPDA, two PDA, two HTM or two TM. Can you decide the languages accepted by them is disjoint? Means there is no common string accepted by given both the machines. Okay, that's the disjointness. 7. So disjointness, I think I can change that order because I have another order. Equivalence, I can use the first equivalence because the table looks nice if I follow this order. Equivalence means the given two machines, are they accepting same language? Then a disjointness. I just explained what is disjoint. So for this you need to have the two machines, like two finite automata or two DPDA, two PDA, something like that. 8. The set containment. Here also two machines or two languages important. Set containment means I'll give you two machines, is a language accepted by one machine, subset of the language accepted by another machine. So that is called a set containment. It's going to be a subset checking property. Okay, they are not closure properties. Remember, closure properties are different. In the closure properties, the input will take from the domain, that will observe after applying the operation where it goes, output. But all these problems you will be having only two things, either yes or no. Everything is given in the data, like all the required parameters will be given. Machines are required, then machines will be given. Languages are required, languages are given. Just you need to observe the property, if that is going to be answer yes or no. Okay, example is finite automata halts on given string. Okay, string will be given, finite automata will be given, so you need to say yes or no, that's it. Okay, if you can say always every finite automata you are able to say yes or no, that means that problem is decidable, because you have algorithm that always, of course, algorithm means halting Turing machine. When you have halting Turing machine for any of this problem, so we are going to worry about what exists. For all these problems, because it is everybody is going to be one problem now. For all this problem HTM exists, then they are decidable. If HTM not exists, they are undecidable. That's all. HTM exists or not. If you have a Turing machine that always solves, that means it is decidable. So when you look at them, for so many problems here you have halting Turing machine. So here decidable. So I'm just going to write tick. Tick mark means HTM exists. Remember, tick mark means HTM exists. HTM exists means decidable. Remember that. HTM exists means decidable. Cross mark means HTM not exist. TM may or may not exist, we don't care. But HTM not exist, it means undecidable. But I'm not saying exactly which undecidable, because undecidable again two types. TM may exist, TM may not exist. Only we are talking about HTM exist or not. Okay, if you really want to know which undecidable, you need to go a little bit deeper to understand each and every property here. Now, I'm just putting tick mark for decidability. Okay. So first column is so easy to remember. This all problems are decidable. So when the input is finite data or regular expression or regular grammar or regular language, then all these problems are decidable. Okay. So you can ask finite data that is that given finite data accepting any string, it's a decidable. Emptiness is given finite data accepting empty language, decidable. Is given finite data accepting finite language, is decidable. Is the given finite data accepting every string in the sigma star? Yes, decidable. Is the given two finite data, are they equivalent? Yes, decidable. Is the given finite data two machines will be given in the finite data, then you need to observe whether the given whether the language accepted by one finite data subset of intersection, what we say, if the languages accepted by two finite data not having any common string, then we say disjoint. Okay, disjoint means what? L1 intersection L2 is equal to empty. If L1 intersection L2 is equal to empty, then we say they are disjoint. So if two machines are given, then identify the language accepted by one machine, identify the language accepted by another machine, then just do the common strings or observe the common strings or do the intersection of these two languages. If it is empty, then they are disjoint. If it is non-empty, they are not disjoint. Okay. Set containment means again two languages or two expressions or two grammars, two regular grammars or two finite data will be given to you, and look at the languages represented by them. If one language, that means one language is inside or subset of other language, that means it is a set containment. If not, non-set containment. So this is decidable, and for this Turing machine, every problem is here undecidable. You cannot build any HTM to understand this property. Okay, these properties like halting problem for TM or membership for TM, these properties are not having HTM. Okay, now look at other things. You can easily remember them. That's why I made this 8 rows specially. For DPDA, it is decidable except last 2 rows. So these 2 rows are undecidable. Okay, PDAs half of 4 rows are decidable and other 4 rows are undecidable. For HTM, first 2 rows are decidable, remaining all undecidable. So you can easily remember these properties based on here all of them, here except last 2, here except last 4, only first 2, here nobody. So very easy to remember this decision properties table. Okay, here I am going to help you to understand these problems and languages, because there are various problems are there. These are only decision properties table, right? There are various languages and problems we are going to deal. Some of the problems which table is not covered, I am writing here. Like I may ask the questions like 1, whether given CFG is ambiguous. This is not covered in the table, right? Because CFG, I'm not going to ask for every column. That's a different grammars are there. Okay, this problem is undecidable. Okay, there is another problem, whether given CFG is unambiguous. Both problems are undecidable. But they are different, because in undecidable there are 2 types of undecidability problems. So these 2, even though undecidable, but one is semi-decidable, other is not semi-decidable. That means one of them will have a Turing machine, other will not have a Turing machine. In this, ambiguous is going to be, you know, when you say context free grammar is ambiguous, for some string you will definitely have the more than one parse-tree, but here every string you will have exactly one parse-tree. So this you may not build, you may not, you know, say yes or no very, you cannot say the S very clearly, but here S means definitely you will find at least one string that has more than one parse-tree. So every ambiguous grammar you will find a reason, but if it is not ambiguous, you don't know why it is. Okay, you may or may not find the reason. So here at least S will have a logic. That's why for this problem especially TM exists. TM exists means which is RE but not recursive. But this one even TM not exists, so not RE. So these two are even though undecidable problems. These two are even though undecidable problems, but this problem will have Turing machine. This problem will not have a Turing machine. So likewise, let me ask some questions here. Third one, whether given grammar, I'm talking about a grammar, is context free grammar. Oh, this is simply you have to look at the LHS is having exactly one non-terminal. If I give you 3 productions, what you do, just look at, let me tell you one thing. See, I have given something here. Okay, 3 and maybe I'm taking more, that's fine. See here, just you have to look at LHS, is it having exactly one non-terminal? See, oh, exactly and only, but here 2 symbols are there, but in according to context free grammar here only one symbol, that one symbol should be only non-terminal. So this is not a context free grammar. See, you have an algorithm that that can always stop. So for checking this whether the given grammar is context free grammar or not is a decidable problem. So this one is a decidable problem. How? Just you need to verify the grammar structure, that's it. How many symbols are there in LHS, what symbols are there, because the rule says exactly and only one non-terminal should be there. And this problem is different from whether given grammar generates context, generates or represents, generates context free language. Oh, this is completely different. And indirectly you are asking, given grammar means grammar is by default unrestricted, grammar name is not mentioned, unrestricted means indirectly you are talking about Turing machine. Is that given Turing machine represents a CFL? We do not know. Given Turing machine represents REL, that's all we know. But which REL? There are in the world, there are infinite Turing machines. We can't use the same algorithm for all of them. So there is no generalized algorithm to understand what kind of language accepted by Turing machine, except we know that Turing machine accepts REL. We cannot check the property of Turing machine. That is reason even unrestricted grammar also we can't check what language it generates. We know only recursively enumerable. Is it regular? Is it CFL? Is it DCFL? Is it finite or is it infinite? We cannot. So this problem is undecidable, and not only undecidable, it's also purely not REL kind of concept. Likewise, there are many problems in the world which are very important. So some of the problems I will be helping you to understand in the coming session. We'll be having some practice session on the undecidability and Turing machine. There I'll be helping you to understand some of the undecidable and decidable languages as well as problems. Okay. Okay. Some questions I'm giving you, so try to answer it if possible for you. Okay, I'm just giving you some language. L is equal to DFA such that language accepted by DFA is equal to pi. Pi means empty language here. So you need to understand what is this language. It is a language, but it depends on the problem. That is emptiness problem. That what is the emptiness problem? Emptiness problem is decidable or undecidable. So that will help you to answer it. Is, I'm writing here, is it regular language? Definitely not, because you are having set of DFAs, not set of the strings like A star, B star. It's the machines you are having, right? It's not a regular language. But is it decidable? Is it undecidable? Is it recursively enumerable language? Choose which of them which it can shoot. It is MSQ type. Okay, I'm giving you only MSQs in this session. So remember all the 5 questions that I'm going to ask here, MSQs. So if more than one option is correct, please let me know that. If L is given like A power n, B power n, such that n greater than or equal to 0. Okay, you know very well this language, right? It is MSQ type again. Is it regular? Is it decidable? Is it undecidable? Is it recursively enumerable language? Okay, so let me know how many options are correct for this language. Okay, very famous problem we have now, that is the language. Let me write a statement first. Write a language, better write a language. TM such that TM accepts epsilon. So this belongs to one of the problem in the decision properties table. So TM accepts epsilon. Whether TM accepts epsilon, that is actually called as a membership, because you're talking about accepting a particular string. So string is given, TM is given. Now this is going to be a membership problem. So what is it? Is it again MSQ type? It is. Is it decidable? Is it undecidable? Even though it is undecidable, sometimes what happens, it might be having Turing machine, we do not know. So you need to understand, is it recursively enumerable? Do you have one Turing machine to understand all the Turing machines in the world? So this is a very important point. REL, and what else? You have REL but not recursive. Okay, it's a very important to understand these lines, because I am asking only implies, is. Here many answers could be correct. Suppose if you got the answer, let's say REL but not recursive. If you got this answer, this one is also called as REL. Of course, this one is REL and this one is also undecidable, because is you are saying, right? So exact name of this language is suppose REL but not recursive. You can say it is REL, it is also undecidable. Okay, if you get this is decidable, then decidable is also called as REL here. So also called as means it's not a synonym here. Is REL, is REL. Every decidable is REL, but REL need not be decidable. Okay, so use that implication statements. Question 4. Whether this is a problem, okay, whether given TM accepts recursively enumerable language. Okay, I did not mention which REL, but it's just some Turing machine and REL. With a given TM, I'm asking, is it accepting REL? Okay, any REL doesn't matter. Is it accepting REL? This problem is it decidable? Is it undecidable? Is it recursively enumerable? Problem it is, okay, not a language. Recursively enumerable. Or is it RE but not recursive problem? Which problem it is? And only you should know, this question is very straightforward. It is a trivial problem and you don't need any proof for this statement, because somebody is asking definition of TM. What every TM accepts in the world? Is it regular? No, right? Is it CFL? No, right? every TM in the world should accept REL. The question is very simple. Are you student? Yes, you are the student. So for that, you just require a definition of a student, definition of TM here. So TM accepts REL or not. That's by fact, by definition, every TM should accept REL. So what kind of, it's MSQ again. It is MSQ. But don't try to choose one statement. Sometimes multiple statements could be correct. Okay, last question here. Complement of a recursively enumerable language is dash. Okay, it is again MSQ. First answer may or may not be REL, recursively enumerable language, REL represent, may or may not be REL. Another one, either recursive language or not REL, either not REL or recursive. Last one, never be REL but not recursive. So what will be the complement of it? Option D is recursive. So which one will be the right option? It is MSQ. Again, more than one option could be correct. So cross check the statements. Yeah, thank you so much for watching this video, and see you in the next, and that will be the last session. We'll be having practice on Turing machine undecidability in the coming session. See you, take care.